hope or sleep over it. So today's topic is going to be on graphs. Okay. So actually graphs is normally a very big topic, but in yours, according to your syllabus, it has been just reduced to like 2-3 main topics. Okay. So we are going to do only that much. What is there in your syllabus? So basically, we'll see what is a graph, and today all the definitions on graphs. Okay. And then tomorrow's lecture will continue. So y'all can keep a I'll share this document with you. I've already shared, but the definitions are not shared, but I'll share the definitions with you. So you can just note down in brief little bit so that you understand as I'm explaining the rest of the slides so that you understand the definition. Okay. And no need to note down word by word. I'll share with you the PDF for this. So basically what is a graph? Okay. So the graph is a collection of two sets where V and E, where V is the set of vertices and E is the set of edges. So in a graph, an edge is nothing but it's a line which connects two vertices. So for example here, you can see this is a graph, an example of a graph. So the vertices are normally drawn with the help of like this circles, okay, and inside that you can write some name for the vertex, okay, and any connection between the two vertices, that connection, the line between the two vertices will be known as a edge. So the circular things will be known as vertices and the connection between the vertices will be an edge. Now in a graph, the vertices need not be always connected. So I could have something like this. Okay, this is a valid graph. I could have two vertices which are connected and a third vertex which is not connected. Okay, so you can think of this like two cities, and this is a island. So this is the sea in between. So normally graphs could be used to represent anything. Okay, so like for example, this could be representing two cities like say Mumbai and Delhi. Okay, maybe this is representing the continent Africa and this is the sea in between. Okay, so something like that. So graphs could be used to represent basically anything. So there are two types of graphs: undirected graph and directed graph. So undirected graph means something like this. Okay, it has an unordered pair of vertices. So what you mean by unordered? The vertices are connected by lines like this, and these lines are not having any arrows. Okay, there are no arrows on these lines, they are just plain lines. You are having the vertices are connected by plain lines. There is no arrows on these lines. So that is the meaning of unordered. Okay, so if this is the name of the vertex V0 and this is V1, okay, this edge I can call it as V0 comma V1 edge. The name of that edge will be V0 comma V1, or I could have called it as same edge, I could have called it as V1 comma V0. Okay, so this same edge could be known by both this name. Therefore, I am calling it as a unordered pair. Two vertices are involved in an edge. Therefore, it's a pair. Okay, there is no order. I could have called it as V0 V1 edge or V1 V0 edge. Okay, please remember this. So you can see here the two sets are defined here, the set of vertices and the set of edges, okay, of this graph G. So there are four vertices V0, V1, V2, V3. So I have mentioned it here: V0, V1, V2, V3, all the four vertices. and the edges between them. So here you can see the first edge, V0 to V1. So once you have mentioned it as like this, you need not mention that other name also. Just mention any one of the two names. Like I've already told you, this edge could have been known as V1, V0 or V0, V1. So once this name has been included, you do not include the second name also. Just include any one of the two names. Okay. Second edge is from V0 to V3. Here V0 to V3. Then V1 to V2. So here V1 to V2. V1 to V3 and V2 to V3. So there are 5 edges and 4 vertices. Okay. So a graph which has unordered pair of vertices is known as a undirected graph. Please remember. And if there is an edge, it can be represented any one of the two ways, U, V or V, U. You have to remember this throughout our next 3-4 lectures. What is an undirected graph and what is a directed graph? Very important. Okay, so going over to directed graph. So like I told you, this is unordered. A directed graph is also known as a digraph, and it has an ordered pair of vertices. Okay, ordered pair of vertices means the direction is defined. So if I say the name of the edge will be U, V, it has to be U, V. Okay, I cannot have the other name. I cannot place and V is the head of the edge. Okay, so for example, you can see here again the number of vertices here you can define. So the number of vertices V0, V1, V2, V3, V4. Okay, there are 5 vertices, and then the edges. While defining the edges, you have to be very careful here. So you're going to define it, for example, here the first one, V0 to V1. So this is your V0. So you can see the arrow is going from here to here, from V0 to V1. So I have to start with the tail. This is known as the tail, and V1 is the head. So you will name the edge as going from V0 to V1. You cannot name it other way. If you name it from V1 to V0, it is wrong. You could have named it if there was an arrow going from here to here like this. Okay, you can have an arrow going like that in directed graph. In this example, it is not there, but you could have had an arrow like that. Then I would have had 2 unique edges. Both of these are unique edges. One edge is going from V0 to V1. The other edge is going from V1 to V0. Both are not same. Okay, because there is a direction mentioned on the edge. Please remember. So in this case, there is just that edge from V0 to V1. So I have defined it here. Next edge is from V1 to V2. Okay. Then from V3, this is V3 to V2. V3 to V0. Okay. Then there is from V4 to V0. Here V4 to V0. And then there is V3 to V4. Here. The total, the number of edges is 6. You can see 1, 2, 3, 4, 5, 6. Okay. So the important thing to know about a directed graph and undirected graph is, here I could have named the edge anything that I wanted. Either it could be V0, V1 or V1, V0. The name could be. Here, depending on the direction, since the edge is going from V0 to V1, the direction is specified. The name has to be V0, V1. Okay, that is the most important difference between these two. So before I proceed and we learn more definitions, do you have any questions for me on this slide? So basically your graph is a collection of two sets, a collection of vertices and a collection of edges. So any questions before I proceed? Okay, let me continue then. So now we look at the various terms that are there in your graph. Okay, you can just note down these terms and write briefly about it, what you can understand. Okay, so here we are going to do with reference to this graphs. Okay, so I'm going to tell you all the definition with respect to this. So I think I've already shared this PDF with you. In case you are having it, then you can refer to it, or you can look to on this also, no problem. So the first definition that you're going to see is weighted graph. Okay, weighted, WEIGHTED. So what is a weighted graph? So if a graph is weighted, then its edges have assigned some non-negative value. Okay, so if a graph is weighted, then its edges will have some non-negative value. And those non-negative values will be known as weights. A weighted graph is also known as a network. So for example, here a graph G9, this is your graph G9. You can see here, this is a example of a graph. So here you are having vertices V0, V1 and V2. Okay. So all these vertices are connected by edges. Okay. Now, one thing that you can notice is it's a digraph or a directed graph because there is directions. So this is a digraph. And second thing you can notice is on these edges that are there, some non-negative values are mentioned. Okay, some non-negative values are mentioned. So any kind of a graph which is having some non-negative values mentioned is known as a weighted graph. So these values could represent cost, length or distance. So for example, if these were two vertices and they were used to represent say two cities, okay, say this was Mumbai, say it was Goa, then I could say maybe it can take me 9 hours to travel from Mumbai to Goa, something like that. Or I could say, or the cost of traveling between Mumbai to Goa is 9, or it takes me something. So it could be length, distance or cost, anything, time. Okay, so any specific value that you want to associate with these edges, that you can associate. But all these numbers then will represent that same thing. You cannot have one edge as time and the other edge as cost. If you define this as a time, then this will be time for all the edges. Okay, so this was your first definition. Second definition, subgraph. So basically, it's just for understanding, a graph H is said to be a subgraph of another graph G if and only if the vertex set of H is subset of vertex set of G, and edge set of H is a subset of edge set of G. So if there is a subgraph H and there is a graph G, then these vertices and edges of this graph will be the subset of this. Then we call this as the subgraph of G. Okay, the vertices and edges of H will be the subset of vertices and edges of G. Then H is the subset of G. Third definition, adjacency. Okay, you can note down this. This is very important. Note down the example at least and understand this. Adjacency. Okay, adjacency is a relation between two vertices of a graph. So a vertex V is adjacent to another vertex U if there is an edge from vertex u to vertex v. Okay. So for example, in G2, this one, okay, we'll see which are the adjacent vertices. So according to the definition, we say two vertices are adjacent if there's an edge from one vertex to that other vertex. There should be a direct edge, okay, no indirect edge. So if you compare this vertex V0 with say this one, okay, then we will say that these two are adjacent to each other. This is V0 and V3. This is V0 and this is V3. So I will say vertices V0 and V3 are adjacent to each other because this edge is there connecting them. Okay, so that name of that edge could be V0 comma V3. So I will say V0 and V3 are adjacent to each other because of this edge. Okay. Now, like I told you, this edge could also be named as like this V3 comma V0. So I could have said because there is an edge present from V0 to V3 and from V3 to V0. It's the same edge. Therefore, these two vertices are adjacent to each other. Okay. Can you tell me if in that same graph, if these two vertices are adjacent to each other, V0 and V1, you can type in the chat. Are these two vertices adjacent to each other, V0 and V1? No, correct. No, because there is no edge between them. What about these two? What about this and this? Okay, this is V4, this is V4 and this is V1. What about this? Are they adjacent? Yes, they are adjacent because there is an edge that is present between them. Now, this what I told you was for a undirected graph. Okay, let's see for directed graph how you find out whether they are adjacent. Okay, so in a directed graph, if u comma v is an edge, then v is adjacent to u. Okay, so if suppose this is the edge u comma v, then we say that v is adjacent to u, but u is not adjacent to v. Okay, please remember. So if in a directed graph, if I say this is the edge, then I will say that v is adjacent to u, but u is not adjacent to v. Okay, this is true, v is adjacent to u, but u is not adjacent to v. So here you can see, if you look at this graph G5, okay, okay, when you read it, actually it's a little bit confusing for you. So when I'll just repeat this again, so just understand. Okay, so when I'm saying this, v is adjacent to u, but u is not adjacent to v, but we will say that u is adjacent from v. Okay, u is not adjacent to v, but U is adjacent from V. So if you look, it means the same thing actually, okay, but the way it's defined in your textbook, I'm telling you. So if we say V is adjacent to U, but U is not adjacent to V, but this is true, we can say that U is adjacent from V. So basically, if you look at this example here for these two vertices in graph G5, then I will say that V1, I will say that V0, V1 is adjacent to V0, and I will say that V0 is adjacent from V1. Okay, so I will say that V1 is adjacent to V0 and V0 is adjacent from V1. Okay. I hope you're getting it. Let's just take this example. For example, in G6, here I will say V2 is adjacent from V0, or V2 is adjacent to V0, and V0 is adjacent from V2. Okay. So basically, I'll just simplify it for you from what they have told you in the textbook. What you're going to do is, whether it's a directed graph or undirected graph, okay, as long as the two vertices are connected by an edge, okay, there's an edge between the two vertices, then we will call these two vertices as adjacent. Okay, in simple words, I'll tell you, this is the way you interpret it. Okay, you try to actually read the definition and the English of it, you will get confused. Okay, so please remember it like that, it will help you. So as long as there's an edge between the two vertices, whether it's a directed graph or a undirected graph, you will call those vertices as adjacent to each other. Okay, next definition, incidence. Okay, again this is the important definition. I'll read the definition for you. Definition again, like to remember is difficult, but I'll tell you the way to understand it. So I'll read the definition. Incidence is a relation between a vertex and an edge of a graph. In an undirected graph, the edge u comma v, is incident on vertices u and v. Okay, is incident on vertices u and v. So for example, if you take this graph G2, then this edge v0 comma v3 is said to be incident on the vertices v0 and v3. This is v3. So I will say that this edge is incident on the vertices v0 and v3. Okay. So basically what it means is, incident means what? When you write that edge, now suppose I would tell you to write the name of this edge, then you would have written the name of this edge as v0 comma v3. Yes, you would have written this edge. So now if I tell you what is an incident edge on these vertices v0 and v3, so basically what you would do is, given this graph, you would write down all the edges. Okay, so the other edge that is possible in this graph is v3 comma v2. So you would write down these edges. There are just two edges. Now I ask you, which are the edges which are incident on v0 and vertex v0 and vertex v3. Then you check, these are the two edges that are possible. Which edge contains both these vertices? Which edge contains both these vertices? So out of these two edges, you will see that only this edge contains both the vertices. Okay, so you would call this edge as the incident edge on these two vertices v0 and v3. So that is the meaning of this incidence. Incidence means the edge contains those two vertices. If I ask you which is the incident edge on vertex v2 and v3, then again you would check the edges and you will find out all the edges. You would find out all the edges which contain these two vertices V3 and V2, and whichever edges contain the vertices V3 and V2, then I would take that edge. So in this case, there is just one edge which contains both the vertices. Suppose I change my question, okay, and I want you to answer in the chat. Suppose I ask you, which are the edges incident on the vertex V3 from this diagram, from the graph G2? Then what would you say? Which are the edges incident on this vertex V3? That means which edges contain this vertex V3? So here this is V0, this is V3, and this is V2. So you can write the names of the edges which contain the vertex V3. Write it in the chat. So those are known as incident edges. Edges incident on vertex V3. Yeah, V0, V3 and yes, V0, V3 and V3, V2. So all the edges which contain the vertices V3, which contains the vertex V3, will be known as incident edges. Okay. Siddesh, I hope I answered your this question because I had clarified about it. In case you have not understood, you can ask me again. Yeah, so just to make you all clear, let's do some more. Can you tell me the edges incident on this vertex here? On vertex V1, this is V1. Okay, so this is 1, this is 0, V0, this is V3, this is V4. So which are the edges incident on V1? Only find the edges which are incident on V1. So if you want to find out the edges which are incident on V1, again I'm repeating, you have to mention all the edges that are containing this vertex V1. So you can see there are how many edges are connected to V1. There is here there is one edge, here there is an edge, and here there is an edge. These are the edges which are connected to V1. Any other edge is connected directly to V1. We want only direct edges. So you will have basically 3 edges. Can you name them based on what I have told you previously in the lecture? Can you name these edges? This is V0, V3 and V4. The V1. V1. Can you name these edges which are incident on V1? Yes. Now when you are writing, you please need to put brackets. Okay, you all are all naming these edges correctly. Now what you need to do is you put brackets. Okay, so I'll just tell you how to do it. So what you're going to do is put the brackets. So now for example, these are the edges that you all have mentioned. So this is the first one. Okay, so it is going from V0 to V1. Its direction is from V0 to V1. So you will put a comma here, V0 comma V1, and put brackets like this. Second edge is going from V1 to V3. So the name of that edge will be V1 to V3. Okay. Third edge is going from V4 to V1. So the naming has to be correct. V4 to V1. So these are the three edges and these are the names from where it starts to where it goes, the direction. That's why the name will be like this. I cannot name this as V1 comma V4 because the direction of the arrow is like this. Okay, so these are your incident edges on vertex V1. Similarly here, suppose I would ask you on V1. Suppose I would ask you in this example. Then you have one edge that comes like this. You have an edge going like this. And one more edge which comes like this to V1. The V0, V2 and V1. Okay. So the name would be, here there are two edges in both the directions. So here you would have the names of the three edges would be V0, comma V1. Okay, that is this edge V0, comma V1. Then you would have had V1, comma V0. This edge V0, V1, comma V0, and then you have V2, comma V1. V2, comma V1. This would be the edges incident on V1 in this example here. So I hope you are getting it. So let's continue. Next definition is a path. Okay, definition of path. So a path from a vertex U1 to vertex UN, from vertex U1 to vertex UN is a sequence of vertices U1, comma U2, comma U3, till UN. So a path from U1 to UN is a sequence of vertices U1, comma U2, comma U3, till UN. And the length of the path, suppose you want the length of the path, the length of the path will be given by the formula n minus 1. Okay, let me show you an example. So suppose I want a path here in this graph from V0 to V2. Then I would name this path. Okay, I want a path from V0 to V2. So it's a sequence of vertices. So I would start from here and I would find one path. Okay, I would start from here. So I would go from V0 to V1. So I would write here V0 dash V1. Okay, and my final destination is V2. Then from V1 I would find a path to V2. So I would write V0, V1 and V2. Now if I want the length of this path, then how many edges are connecting this path? There is one edge here and another edge here. So the length of this path would have been 2. Okay, length of the path would have been 2. Now the question is, many of you must be having the question, is there always a unique path? Or is there only one path between two vertices? Depends on the type of graph and depends on the number of edges. Okay, there need not be only one single path between two vertices. So for example, I want to, in this example you can see, I want the path from V0 to, say I want from V0 to V2. Okay, can you all find out the paths? There could be multiple paths. Please note, there could be multiple paths. So can you find out at least more than one path? At least two paths can you find out? There are many different ways of coming to V2 from V0. So you're going to start here and you're going to end here. And there are so many different ways of doing that. So can you find out? At least two different ways of coming from V0 to, starting from V0 and ending at V2. Yeah, are you all typing the answers? Yes, V0, V1, V2. Okay, V0, V1, V2, or the second answer could be V0, V2 directly. Okay, V0, V2 directly, or you could have come V0, V1, V2. So there are many more other paths. If you look at the combinations, there are many other paths. Okay, so just to show you some paths, you could have started V0 and directly gone this way and gone to V2. Okay, so length of this path would have been 1. Okay, only one edge is there. Second way you could have gone V0, you would have gone to V1, and then you could have gone to V2. Length of the path would be 2 because there are two edges. Okay, V0, V1, V2. So you could have gone V0, you could have gone to V1. Okay, and from V1 you would have gone to say V3, and then from V3 you would have gone to V2. Okay, finally you want to go to from V0 to V2, so it does not matter from where you go. I found this path V0 to V1, V1 to V3, okay, and V3 to V2. So length of this would have been 3. So there are so many paths like that. Okay, I'm sure you all can make out how many paths are there. There are many. Okay, so I hope you have got understood what is path and what is length of a path. So you can see here from each of this, if the number of vertices here, number of vertices is suppose n, then the length of the path is n minus 1. So you can see here the number of vertices in the path is 2, and the length of the path is n minus 1, that is 1. Then here there are 3 vertices, length is 2. Here there are 4 vertices, the length is 3. So if depending from this, the number of vertices in the path, you get the length of the path also. Okay. Then next definition, reachable. Next definition that you need to know, reachable. Okay, reachable. So if there's a path P from a vertex U to vertex V, okay, if there's a path P from a vertex U to vertex V, then vertex V is said to be reachable from vertex U via the path P. Okay, so if there's a path between two vertices, then we say that the two vertices are reachable via that path. So you can take any example. So say take this example here. Okay, take this example here, and here we are having, this is V3, okay, this is V2, this is V0, this is V1. So if I want to know whether vertex V3 is reachable from vertex V1, what will you do? You will check if there's a path. There should be at least one path from between these two vertices. Okay, so you can see that there is a path from here to here, from V1 to V3. Therefore, I will say that V3 is reachable from V1 via this path. Via this path, V1 dash V3. Okay. So same way, if I ask you, is this vertex reachable? Is V1 reachable from V2? The obvious answer for it will be what? Is this vertex V1 reachable from V2? Is it reachable? Sorry. Is vertex V1 reachable from, sorry, yes, is vertex V1 reachable from V2? No. Okay. Why no? You must know the reason. There is no path between those two vertices. Okay. As you can see here, these examples of various graphs here, that this is also a proper graph. although you can see there's no connection between this vertex with these other vertices. Okay, but still this is a graph. Okay, so again, going back to this definition, is just you have to remember that a graph is a collection of these two sets, where B is a set of vertices and E is a set of edges. We have not said that the vertices and edges should always be connected. We just say that there is a set of these two. So when I ask you, suppose I would tell you to write down the number of vertices and edges for this graph, then you would write the set of vertices here as 4. All these 4 are the set of vertices for this graph G2, and the number of edges are just 2, these 2 edges. Okay, next definition, simple path. Next definition is simple path. So simple path means all the vertices in that path are distinct. Okay, all the vertices in that path are distinct. So for example, in this graph G12, okay, I just name this first. This is V2, V3, V0, V1, V4, V6 and V5. So now if you are told to find a path, a simple path. So basically a simple path, in that path all the vertices has to be distinct. You cannot repeat those vertices. So for example, you can see V0, V0 dash V1 dash V3, V4 and V6 is a simple path. Here you can see V0, V1 to V3, from V3 to V4, V4 to V6. This is a path from V0 to V6. But if I would give you this path, can you tell me whether it's a simple path or not? So suppose it is V0, V1, V3, V4, V6, V3, V2. Is this a simple path? Yes or no? If no, then why? In the same graph, I am referring to this graph itself. Is it a simple path or not? No, no, correct, no, because V3 repeats, and I told you simple path, there is no repetition of the vertices. Okay, so remember when we are calling for a path, the path we can have this vertex repeated. So if I ask you whether this is a path, yes, it's a path, it's a valid path. Okay, it's a path. But if you ask you whether it's a simple path, no, it's not a simple path, because this V3 is repeating. Okay. Okay. Going to the next definition. Next definition is of cycle. So in a diagram, a path u1, u2, un is called a cycle if at least two vertices and the first and the last vertices are the same. Okay. So basically, in a cycle, two vertices repeat, at least two vertices repeat, and you expect the first and the last vertex in that path to be the same. Okay. So you can see in this graph G7, for example, in this graph G7, okay, this path will be known as a cycle. So V0 to V2, V2 to V1, V1 to V0. Okay, so V0 to V2 here, V2 to V1, and V1 to V0. Okay, so cycle definition is you have found a path, and this vertex, the first and the last vertex is the same. Okay, so the path should have at least two vertices. The path should have at least two vertices. So you can see here the total number of vertices in this path is 3. There is V0, V2, V1. So there are 3 vertices, and the first and the last vertex is the same. Then we call it as a cycle. Okay. Can you find out a cycle here? Any path here which is a cycle? So can you show me a path which is like the first vertex and the last vertex should be the same? And the path should contain at least 2 vertices. Are you trying? Okay, let me tell you then. So you can look at this path. Okay, this is V0. So take this path V0, V1. Okay, V0, V1. Go to say V2, and then go back to V0. So when a path starts and ends at the same vertex, then we call it as a cycle. Okay, or there are many cycles here. Another cycle could be you could start at V3. So like this, V3 to V0, V0 to V1, V1 to V2, V2 to V3. So when you have a path that starts and ends at the same vertex, it is known as a cycle. Next definition, simple cycle. Just like a simple path, simple cycle is having the same meaning. So we call a cycle as a simple cycle if all the vertices in that cycle are distinct. Okay. So if you find out a cycle and there are no repeating vertices besides the first and the last vertex, there is no repeating vertex, then we call that cycle as a simple cycle. Okay. Next definition, cyclic graph. But please do not, for example, this one here, just take this example. Once you suppose there is no cycle here, so this type of a graph will be known as a acyclic graph. So a graph in which there are no cycles will be a acyclic graph. So in this slide here, the graphs G2, G4, G5, G6 and G8 are not having any cycles. You can check. Okay, you can check later. These graphs are not having any cycles. So these are known as acyclic graphs. Whereas the other graphs that are present on this slide are having at least one cycle. So they are known as cyclic graph. Then next you must know what is this DAG. This stands for directed acyclic graphs. So here we have studied what is a directed graph. So if a directed graph is acyclic, then we call it as a directed acyclic graph. So here G5 is an example of this directed acyclic graph. Okay, it is acyclic and also directed. Similarly, you can call a G6 and G7 also. They are directed and they are acyclic. So they are directed acyclic graph. Next definition, degree. So degree is the number of edges that are incident on a vertex. Suppose if I want to know the degree of a vertex, is the number of edges incident on that vertex. If you remember in the beginning of this lecture, I told you what is incident edge. Okay, so incident edge means number of edges containing that vertex. Suppose I want the degree of, say, this vertex V1. Then you will find out how many edges are containing this edge V1. So there is one edge here, one here and one here. So there are 3 edges containing, or 3 edges that are incident on V1. So therefore the degree of V1 edge or degree of vertex V1 will be, degree of vertex V1 is equal to 3. Okay, how I get this value 3? There are 3 edges containing V1. There are 3 edges which are incident on V1. Next definition, in degree. So in degree of a vertex V is the number of edges entering the vertex V. Okay. So for example, in this graph G8, the degree of vertex V0, the degree of vertex V0, this is vertex V0. So it's not the degree, I was telling about in degree. So the in degree of vertex V0 will be 0. Okay. Why? Because there are no edges that are entering V0. By entering, what I mean, this is V0. So all this, if there were any edges that were like this entering, then I would have counted those edges and I would have said the in degree of V0 is that many number of edges. You can see here all these edges are leaving V0. They are all leaving V0. So the in degree of V0 is 0. Okay. Similarly, the in degree of V1 is 2. So if you see at V1, this is V1 here. How many edges? There are 3 edges that are linked to V1. So 2 are entering V1 and 1 is leaving. So I am asking you the in degree of V1. So the in degree of V1 is 2 because there are 2 edges that are entering V1. There are 2 edges that are entering V1. So the in degree of V1 is 2. Next definition, out degree. The out degree of vertex V is the number of edges leaving that vertex. Okay. So if I ask you the out degree of this, for example, V0, How many edges are leaving? There's one edge that is leaving, second edge, third edge. So the out degree of V0 is 3. Okay. Similarly here, if you look at this vertex here, out degree of V5 is, there are 3 edges that are leaving. So the out degree of that is 3. Okay. Here again you can see what is out degree of this node. There are no edges that are leaving this. So out degree of this node is 0. Okay. So in simple terms, degree of a node is equal to in degree of a node plus out degree of that same node. Okay. So number of edges that are entering the vertex plus number of edges that are leaving that vertex is equal to the degree of that vertex. Next definition, source. Okay, I think your lecture is time up, but there are just some 5-6 definitions. I'll quickly finish it. Okay, source. A vertex which has no incoming edges but has outgoing edges is called a source. So for example, in this here, vertex V0 and vertex V5 has no incoming edges but has outgoing edges. So they are known as source. Next one is sink. Sink is, it has no outgoing edges but has incoming edges. So for example, in this diagram here, this V tree, okay, it has only incoming edges, no outgoing edges. So therefore V tree is an example of a sink. Then next, pendant vertex. Pendant vertex. A vertex is said to be a pendant if its in degree is equal to 1 and out degree is equal to 0. So if you find any vertex where the in degree is equal to 1 and out degree is equal to 0, then it's a pendant vertex. Then next definition, isolated vertex. If the degree of a vertex is 0, then it is called a isolated vertex. Okay. So in this here, if you find out a degree of this, there are no edges connected to this. Therefore, this degree of it is 0. Therefore, it is known as a isolated vertex. Then next definition, successor and predecessor. In a digraph, if a vertex V is adjacent to vertex U, then V is said to be the successor of U and U is said to be the predecessor of V. So for example, here in G8, V0, this vertex V0, and if you look at this V1, then V0 is the predecessor of V1. Okay, V0 is the predecessor of V1 and V1 is the successor of V0. Then maximum edges in a graph. For an undirected graph, maximum, the formula is given like this. If there are n vertices, then the formula for the maximum number of edges is given by this. For an undirected graph. And for a directed graph, the formula is n into n minus 1. So for undirected and for directed. Then next definition, complete graph. A graph is complete if any vertex in the graph is adjacent to all vertices of the graph. Or we can say that there's an edge between any pair of vertices in the graph. So for example, this is a complete graph. Because if you apply this formula, you apply this formula, then this formula will be true, in other words. Okay, it has the maximum number of edges. That many vertices are there, 4 vertices, and you'll find this many number of edges. And similarly for a directed graph. So whenever it is true, then we call it as complete graph. Between every pair, there will be a connection. Okay, in simple words. Multiple edges. If there is more than one edge between a pair of vertices, then the edges are known as multiple edges of parallel edges. So you can see here, there's an edge here, and there's one more edge here. These are known as multiple edges of parallel edges. Then next definition is a loop. An edge is called a loop or self edge if it starts and ends on the same vertex. So you can see here, the edge is starting and ending on the same vertex. So this is known as a loop or a self edge. Next definition, multigraph. A graph which contains a loop is known as a multigraph. Simple graph. A graph which does not contain a loop is known as a simple graph. Regular graph. A graph is regular if every vertex is adjacent to the same number of vertices. This is an example of a regular graph. Since every vertex is adjacent to 3 vertices, you can check. It is, for example, this V0 is adjacent to V1, V2 and V3. And every other vertex is also adjacent to 3 vertices. You can check for yourself. Next definition, planar graph. A graph is called a planar graph if it can be drawn in a plane without any 2 edges intersecting. Okay, this is not a planar graph because the edges are intersecting. Whereas these are your planar graphs. And the last definition, null graph. A graph which contains only isolated vertices. So for example, something like this, say you are having isolated vertices, then that graph will be known as a null graph. Okay, so these are the terms associated with your graphs. So among all these terms, the most important that you need to know are the cycle, incident, adjacent, in degree, out degree. Okay, and the formulas for this maximum edges in an undirected and directed graph. Yeah, the other definitions are important, but these are the ones we'll require in the next lectures. Okay, so I'll share this PDF with you and you can go through these definitions again. If you have any questions, tomorrow's lecture we can solve those questions. So we'll stop for now. Thank you everyone.